Okay, so yesterday we did some textbook material to set the foundations for what is going to be today algorithms, optimization algorithms for machine learning. I just want to put again one slide that was there yesterday. And this slide is sort of an X-ray decomposition of what the Newton direction does. And I'm going to use it because in a moment we will not be using exact Hessians, but stochastic Hessians. And the question is, what is going to be the meaning of this sort of semi-stochastic Newton method? So just to remind you, if we take the Hessian matrix and make an eigenvalue decomposition of it, so this is an eigenvalue corresponding eigenvector. Any symmetric matrix can be decomposed in this spectral way. What is very convenient about this is that now I can write the inverse of that matrix by simply taking the reciprocals of the eigenvalues. I have now an explicit representation of the inverse, and to compute the Newton step, I take the inverse matrix and multiply it by the gradient. So let's take this matrix multiplied by the gradient, and I see that the Newton direction is a linear combination of the eigenvalues of the Hessian matrix with some weights that in general, we don't know what this term is going to be, but in general, the weights are going to be inversely proportional to the eigenvalues of the Hessian. The smallest eigenvalues will give the larger contribution to the Newton direction. So the Newton direction is going to be biased along the directions of the smallest eigenvalues, and this is why it's so difficult to reproduce the Newton direction, because the smallest eigenvalues are the ones that are more difficult to compute. Now, what happens if we don't have the exact Hessian? If we compute a Newton step with some other Hessian? Well, the same thing will be true. Let's pretend that this matrix is the Hessian of something else, like a stochastic approximation. Then the Newton step will be a direction that is biased along the smallest eigenvalues of that stochastic Hessian. And what I want to make sure is that if I do things economically, instead of working with a true Hessian, I work with some approximation, that the small eigenvalues of that approximation are valuable. The small eigenvalues reflect the small eigenvalues of the true Hessian. And so the Newton direction will turn where it should be. And we'll also have the right length. Okay, so today I'm going to talk about how to make Newton's method practical for machine learning applications, replacing Hessians, doing dynamic batching, applying it to L1 terms, and then I'm going to give you as a test case the performance of these methods on inverse covariance estimation problems, which are matrix optimization problems. So at the end, I will jump into something more difficult, which is matrix optimization. I'll use some concepts of duality, optimality conditions, and that I'll have to skip, but I will explain how the optimization ideas carry through. Okay, one picture that you have always all of you have seen in textbooks and in here, I want to emphasize it. So this is the official picture of the steepest descent method. The steepest descent method always works like this, unless you're extremely lucky and you start exactly along an eigenvector here or there, in which case you converge in one step. Even if you start an epsilon away from this position here, the steepest descent method will oscillate in that manner and will have a linear rate of convergence that depends on the condition number of that matrix. Okay, fine. So steepest descent can be very slow for problems that are not well conditioned. How about the coordinate relaxation method? Steve Wright mentioned that in several contexts. I'm going to use it because I want to need it for two different reasons. But the first picture is the following. Suppose that the contour lines of your objective function are elongated ovals, ellipses, but their axes are aligned with the coordinate directions. So if the contours are not tilted, if they're like that, and you do coordinate relaxation, and what do I mean by coordinate relaxation? At x0, you move only one variable. And how far do you move it? You move along that variable until you've minimized your quadratic function along that variable. So move the variable x1, you stop here, then move the second variable x2, and you land at the solution exactly with the coordinate relaxation method. Now, what it's doing in this particular case it's doing what is called increasing subspace minimization property. When I move from here to there, I have minimized the quadratic along this subspace. And then I minimize it along that subspace. And because these two subspaces give you Rn, you find the exact solution. OK, so in that case, it has a nice property. But what happens if you tilt the quadratic? Now, the quadratic that I had in the previous slide has a diagonal Hessian. A general quadratic function looks like this if it has a non-trivial Hessian. Now, what happens if you try the coordinate relaxation method? If I start here at x0, minimize along the first coordinate direction, minimize along the second coordinate direction, and so on, it turns out you don't terminate in 2 steps anymore. You're going to have to do an infinite number of steps to minimize a quadratic using the coordinate relaxation method. It no longer has the subspace minimization property. The minimum of this function along the x-axis is here. But the method didn't go there, it overshot. And the minimum along that axis is at this level, and it stops short of that. OK, because of that reason, one should be a little bit concerned about people who propose to use coordinate relaxation methods. There are nice complexity results, there are stochastic results, and so on. But most quadratic functions that one encounters in machine learning applications don't look like that. They don't have diagonal Hessians. They have complicated Hessians. And therefore, the coordinate relaxation method is not going to be very effective. It's not going to be much better than steepest descent at all. Steve Wright gets some complexity results about this. What works, what always works, is to generate conjugate directions. Not coordinate directions, but conjugate directions. And this conjugate gradient method was developed by Hestenes and Stiefel in the 1950s can be explained by this picture that was shown to me by Hestenes, the developer of the conjugate gradient method. I'm that old that I attended a lecture, and he said, look, here's the geometry that you should remember. Conjugate is written usually algebraically. How do I move? If I have a quadratic function, how do I move in such a way that I know that I will terminate in 2 steps? Now, here's the key. Take any point and take any direction. Here's any direction that you choose. Now, replicate that direction, parallel direction, in some other place. Then minimize your quadratic function along the first direction. That gives you this point here. Minimize the quadratic along this direction. That gives you that point there. Join the 2 minimizers, and the line that goes between them is going to go through the solution. And so if you minimize the quadratic along that direction, you get the solution. These 2 directions here are not orthogonal. They're not related by gradients. They're conjugate. And for any n-dimensional problem, this will be true. So you can interpret now going to the solution as having moved along this direction, minimizing, and then creating this conjugate direction that I created here by drawing an artificial line. You can create it by the conjugate gradient recurrences. They give you the second direction, and you terminate that way. And this method has an increasing subspace minimization property. It has minimized the function first along this subspace and then along that subspace. And this is why it's able to terminate in n steps. OK, so that was the main property that I want to discuss. Now I want to go back to the concept of subsampling. And we're getting into machine learning now. Hessian matrices are too difficult, too expensive to compute. And in a moment, I'm going to show you experiments with logistic regression problems that I obtained from Google. The original problems have about 1 million variables, 100,000 and several million training points. So the Hessian matrix, in principle, has like 1 million by 1 million matrix, which is dense. And we want to do Newton's method. How can you do Newton's method on such an unwieldy matrix? Well, the answer is we're going to take into consideration the fact that we're solving a stochastic optimization problem. But OK, the idea is going to be as follows. Suppose that this line represents the number of training points that you have. Here's 1 training point. You can use 1 training point to do optimization, and that gives you the stochastic gradient method. You can use all the training points. It gives you a full batch method. Now, what is the benefit of using the full batch method? I evaluate the function using all the information that I have. functions look like that, loss functions, with the sums of all the training points. Well, the advantage that there is in using a lot of batch points is that you can parallelize a function evaluation. So a method that is being tried everywhere, both for deep learning and all sorts of machine learning applications, is to simply take a significantly large batch. When you evaluate the function, distribute that computation, do it in parallel, and do an optimization step that can be done very cheaply. But you're able to harness easily 1,000 computers, say in a MapReduce environment, to evaluate that function. So this method is competitive, or at least with stochastic gradient descent. And we have this back and forth about what is the best algorithm for machine learning. Is it stochastic gradient, or is it batch methods, and so on? And it goes back and forth. And there are some researchers who publish a paper every 6 months where they change their opinion. It goes from one to the other. And the changing of the opinion also has to do with the parallel computing environment that they use. OK, so this is what this line represents. I'm going to talk now, the concept of subsampling the Hessian means that you choose a certain sample to compute the function and the gradient, and you use a much smaller sample to evaluate the Hessian. And I mentioned that this is possible because Newton's method is very robust with respect to the choice of the Hessian. OK, so suppose that the loss function has a summation form like that, a sum of loss functions, individual loss functions. So I'm going to consider an algorithm that does not use all the training points, chooses a subset of the training points. How do you do that? At random, you take some percentage that you think is important, and then you define a stochastic approximation to your objective function. Right? So the difference between this objective and that objective is that instead of taking all the training points, I'm just using a subset of them. And imagine that I've chosen them randomly. In expectation, the expected value of this function is equal to that function, and so will be of the gradient. Now, let's choose an even smaller sample, a subset of the sample that you use for the function and gradients. And now imagine that we form the Hessian matrix by taking the Hessian of all the individual terms. So if a function is a sum of functions, the Hessian is a sum of Hessians. And so the Hessian now is going to be a summation that includes now a smaller sample set that I call S. And it may be like 1% of the size of the sample that you use for the function and the gradient. And you define this Newton iteration here. So this is a very new algorithm. This is something that has been tried only in the last couple of years. And it looks like Newton's method. And pretty much the only change here is that this Hessian does not correspond to that gradient. They use different sample sizes. And I can be a lot more tolerant here than there. And then let me assume that I take a unit step. There could be a step-length parameter here, but that is not needed. Now, I'm going to choose this sample size for the Hessian so that when I apply the conjugate gradient iteration to solve this problem, it's not going to cost me so much. In fact, so it's going to be fairly cheap. I mentioned here 5%. The sample for the Hessian is 5% of the information that you use for the gradient. And let's say that we just do 10 conjugate gradient steps. When I show you the computations of how Hessian matrix products are done, we will see that a whole cycle of 10 conjugate gradient methods, which require Hessian vector products, if you use only 5% of the information for the Hessian as for the function, this whole cycle of conjugate gradient steps is going to cost you about the same as one function or one gradient evaluation. Therefore, the cost of this Newton-like iteration is going to be pretty much the same as the cost of a steepest descent step. More precisely, it's going to be about twice as much as a steepest descent step. But the properties are going to be totally different. This method is going to have Newton-like properties. And yes? You can imagine that it's the whole training set, or it's just a batch. We're going to do a mini batch. Suppose that X is 10%. x has to be.
Does the size of x have to be significantly larger than the size of s?
Yes, because otherwise, I'm going to show you in this graph, it's not going to be economical to do that. So what is important is that the relative sizes of s and x are intelligently chosen. Okay, so if we do that, so when I say 5%, s is 5% of the size of x. So you first choose your stochastic gradient, say using 10% of all the data that you have. And then you take 5% of the 10% and to compute the Hessian. So that these Hessian vector products are going to be like 5% of what it is to compute the function. But I'm going to be precise about this. So in any case, this method is going to work okay, and it's going to have Newton-like properties. And I can tell you that from my experience, looking at optimization runs for many, many years, to me the distinction between first-order methods and second-order methods can be observed by looking at what step length do you use in order to get decrease in the function. A method that takes unit steps, whatever direction comes out of the algorithm, is good 90% of the time. It's a second-order method. And I call it like that because there's a continuum between using the full Hessian and part of the Hessian. In the steepest descent method, you cannot take 1 times the gradient. Well, you can take it, but it's going to be really bad. The gradient itself does not have any scale. There is something called the nonlinear conjugate gradient method. It produces a certain direction. The unit step length is never the thing that you should take. I don't consider that a second-order method. This strategy that we have here is going to accept whatever step length I get in direction 90% of the time. Therefore, I will consider it a second-order method, even though it's costing just the equivalent of 1 gradient evaluation. Okay, I'm going to get into those details so that all of this is believable. How do we compute Hessian vector products without forming the Hessian itself? Okay, so what stopped people for many years looking at second-order methods for large problems like machine learning is that people said, look at this iteration. Even if I use the conjugate gradient method to solve this linear system, every conjugate gradient iteration requires the product of the matrix times a Hessian, times a vector. And if I do 10 of those products, normally it's going to cost me about 10 times, like 10 gradients. Typically in practice it's going to be more like 50 gradients. So the cost of trying to do a Newton step is going to be like 50 times or more the cost of doing a gradient. And it's very easy to beat steepest descent. Steepest descent, terrible, if you have just any reasonable ill conditioning. But what's not so easy to beat is limited memory BFGS. And that requires only 1 gradient at every iteration. So I have not discussed it here, that's sort of textbook material, but the limited memory BFGS method only evaluates 1 gradient every time, forms a quasi-Newton approximation, and that's what this has to be competing against. So if computing this step costs me 50 gradients, then it's not going to work and it doesn't compete. You'll see in a moment some graphs that I have there. So we have to make this Hessian vector computation more cheaply. Okay, before we talk about cheaply, how do you compute a Hessian vector product without forming the Hessian? Well, if I have a function of n variables and I'm given a direction d, and my goal is to compute the product of the Hessian times a vector, all I have to do is make one observation. What about if we define the function phi to be the gradient of f times the fixed direction d? Consider this as a function of x, where d is fixed. Isn't it true that the gradient of this function, by the way, this is a scalar function, right? So the objective function is a scalar. The gradient is a vector, but the gradient transposed at fixed direction d is a scalar. So I'm considering now is a function from Rn to R given by this dot product. Isn't it true that the gradient of this function is the derivative of this with respect to x, where d is fixed, And that's the Hessian times d. Okay, so what I'm going to do is we're going to code f. We're going to code grad f. And then we're going to code grad f transpose d and differentiate that. And that's going to give me a Hessian vector product without me ever forming a Hessian. Since nobody believes this, here's an example. Suppose you have f of x is e to the x1, x2. What is the gradient of that function? Well, the gradient of this function is x2 times e to the x1, x2, and x1 to e to the x1, x2. It would be that vector with those two components. Then I take that vector and do the inner product with a direction that I now call nu, with nu1 and nu2. So if I take this vector and multiply it times that nu, I get this expression. This is now the scalar grad f transpose d. And all I have to do now is compute the gradient of this function. That is a scalar function. And so you compute the partial of this with respect to x1, the partial of this with respect to x2, and you get that expression. And this is now the Hessian vector product. And I never formed a Hessian. And how expensive is this thing? Well, if I had time, I could argue that if you do it the right way, computing the gradient is never much more expensive than computing the function if you use the reverse mode, which is very similar to backpropagation. So a backpropagation type of algorithm will give you a gradient that's not much more expensive than the function. If you have used similar ideas, the Hessian vector product will not cost you much more than a gradient itself. Now, if you stare at these expressions, all of this is sort of believable. Is this expression Hessian times vector really expensive? Well, aren't a lot of these quantities already as part of the function and the gradient? You can recycle them, right? So if you wrote this code by hand, you would recycle a lot of operations, and you would have a Hessian vector product without a lot of cost. And that's what we're going to do here. Okay, now, suppose that the problem is logistic regression. Then the Hessian times the vector is going to be a summation 2. It's going to have some form. And the key thing is the following. If I have a function that is the summation, then the cost of the Hessian vector product is going to depend on how many points I put in the summation. It's going to decrease linearly with the sample that I use for the Hessian. I can control that completely, directly. The Hessian vector product, then if I take 1%, is going to be 1% as expensive as I use the full information. So it decreases in that way, and this is where we're going to leverage cost. And here's finally the description of this subsample Hessian Newton method. It works as follows. Choose a sample to evaluate the function. And let's suppose that it's fixed for now. Let's assume that the sample size is fixed. I have a huge training set, and I'm going to take the cardinality of x to be 10%. So to compute the function and the grade, I'm going to use 10% of all the information that I have. Then choose a smaller sample, 1% of that. So that's going to be 0.1% of all the information that I have. Solve this Newton step by the Hessian free conjugate gradient method. And what does that mean? That if my objective function was the logistic function, I'm going to code the logistic function, I'm going to code the gradient, and I'm going to code the Hessian vector product. And every time the conjugate gradient method needs the Hessian vector product, I just invoke my routine. Then I get a step D, backtrack if necessary, and then at the next iteration I choose a new sample so that the Hessian is not biased. So at every outer iteration I change this sample that I use for the Hessian, and usually I do that too for the function and the gradient. Now there's a MapReduce implementation of this algorithm at Google. Yes, go ahead.
I'm a little confused about the backtracking. So
yeah.
In terms of the overall work going into the optimization, I naively think, I could be wrong, I naively think that the less information, less data I use for both the gradient and the Hessian, the more likely it is that I'm going to have to be very careful about the backtracking when I try to integrate everything together.
Very good. Great. I'm happy you made that question. Because there is an issue that is a really big research issue, I think. Here's how it works. For any given problem, if you choose a large enough sample for X and for the Hessian, you will get that the unit step length will work all the time. And I start decreasing both continuously, and it will still be the case until I reach a certain threshold. And then everything goes to pieces. So there's a twilight zone here, a really scary place in the world, where you go from the deterministic methods to the stochastic methods. And I don't understand how to go gradually between one and the other. I see stochastic gradient as a Markov process, whereas I look at these as descent methods. And Steve Wright was telling me that he doesn't think that one should use the term stochastic gradient descent. Everybody uses it, so we can't change the culture, because stochastic gradient is not descent. You go all over the place, and then you end up at the solution. But these methods are descent methods. I'm going to give you more detail later about how the performance works. But say for the speech problem I'm going to report in a while ago, we can go to 1% of the original data all the way here, and the sample for the Hessian 1% of that, and still get unit step lengths. Then when we go beyond that, not only do we struggle with the step lengths, but we struggle with the whole algorithm. The Hessian is no longer reliable. We're going in wrong directions. We got into the twilight zone. And that's one part that I really would like to be able to understand. You know, I spent a lot of time yesterday talking about a continuum between steepest descent and Newton. And that's what Newton CG gives you. Is there a continuum between stochastic gradient descent and a batch method? I don't know how to do that. It looks like it's totally different animals, but I'll give you more data then. Okay, so let's look at numerical results. So what did I say here? Oh, there's a MapReduce implementation of this code at Google, but I'm not sure exactly who or why they're using it. It was done a couple of years ago, and it was getting really good results for very large logistic regression problems, using about 1,000 to 2,000 computers. The Hessian sampling approach was beating everything. So let's look at numbers here. So I took a toy version of the logistic regression problem. It has 168,000 training points, 10,000 parameters, and I'm going to use a Hessian subsample, which is going to be 5% of the total. So right now I'm going to use all the training points for the function and the gradient, and the objective function is going to be a multi-class logistic function. NC refers to the number of features, and this is the number of classes. And so that's your form of the multi-class logistic function. And here is the performance of methods. Now, the problem is formulated as a maximization method. So whoever gets up the fastest is going to win. And over here, we are measuring the total number of access points, the total number of times they accessed elements of the objective function. We want to be really fair, because a limited memory BFGS method only computes gradients. A Newton CG method computes Hessian-vector products. So we need to count that in too. But we don't want to report CPU times, because that's machine dependent. Instead of that, we're going to report how many times we access the elements of the objective function. And the results look as follows. If you use a classical Newton CG method, where the sample size for the Hessian is the same as the one for the function, you lose big time. It costs too much, the conjugate gradient cycle. Then if we try the limited memory BFGS method, which is used on many applications, I expect we play with different parameters, and it's sort of not very sensitive, and the subsample Newton CG method does better. Not dramatically better, but does better. I'm going to return to this graph, because there's something here that is very wrong, and we're going to have to fix it. Now, in this graph, we experiment with a number of conjugate gradient iterations that we use inside Newton. So if we use 2 conjugate gradient iterations, I get this performance. 5 and 10, I get better performance. What does that mean? When I saw my student Jillian produce this graph, we were extremely happy. Because what does this graph tell you? that the Hessian information that we devised is useful. The more, the better you solve it, the more conjugate gradient iterations you perform. Not only does the outer number of iterations decrease, but the total amount of work, what this is giving you as a total amount of function evaluations, is decreasing. So you're accelerating the method enough that the additional cost of conjugate gradient iterations is paid off by faster convergence. And beyond a certain point, you don't improve anymore, but this is positive, is very good news. Now here's a graph where we change the sample size for the Hessian. So if the Hessian uses 100% of the training points, 50%, and up to 1%, we keep increasing the quality of the step. And then I didn't report what happens if you go to 0.1%, 0.01%, things fall apart. But there's a regime where things get better and better. And what you really did is you said, look, we have a function of finite variance. Let's look and sample the Hessian, just sample it, touch it a little bit to give me enough curvature information that's going to accelerate things. And that 1% is what's going to do it. OK, yeah?
Yeah, and how fast do you approach to the optimal value?
What's the rate of convergence? Or?
Yeah, I mean, how's the comparison between taking the whole sample or just 1% in terms of approaching the optimal value?
Oh, so this is actually the function evaluation.
Yeah.
So this is the way we're approaching it.
Yeah, but
not in terms of x minus x star, but in terms of maximizing the likelihood.
I know that's what I'm asking. In terms of x minus x star, how is that comparison?
Yeah, so it's going to be a linear rate of convergence for all the cases, and the constant of the rate of convergence is going to be slightly smaller as we use less information. But they're all going to be linearly convergent. Yeah, this is a very good sentence. So now let me tell you why. What I don't like about this. And we're going to fix it pretty soon. OK, so this subsample Newton method beats limited memory by some amount. But this behavior down here is not acceptable. They're starting almost in a similar way. I really want to have even batch optimization methods that start as fast as stochastic gradient. Why does it take so long? Because I'm taking a lot of time to evaluate the gradient, right? And a stochastic gradient method takes just one element, starts doing work right away. And as we will see in other graphs, it starts very steeply here. So I'm going to have to bring another idea, and that is to say, why are we using so much information for the function and the gradient at the beginning? Shouldn't we be varying that so that we can start like a stochastic gradient method? Now, one more technical question. I said that we do 10 conjugate gradient iterations or 5 conjugate gradient iterations. How do you know how many iterations to do? Is there a rule? Well, I'm going to propose something here. And the way my Google colleague will never post it is, suppose you have a quadratic function that has Gaussian noise. And you're going to apply the conjugate gradient method to minimize it. So if there is no noise, the conjugate gradient method minimizes this in n steps. If there is Gaussian noise, how many conjugate gradient iterations are advisable to get an approximate solution? And look at the following derivation. This is going to be sort of algorithmic. It's not going to be theoretical, but it's going to be pretty clean. This is the subsampled Hessian Newton iteration. Now, I don't solve this system exactly. I apply some iterations of conjugate gradients, and I'm going to reflect that by residual RK. I want to know how to control that residual. In order to do that, how about if we write the classical Newton iteration? So here's a Newton iteration where I'm using the same sample for the Hessian and for the function. And let me call that residual R super X. Now, by adding and subtracting this Hessian with a sample S, adding and Okay. This should be a minus sign here. Okay, so please just imagine that's a minus sign. So by adding and subtracting that term, this expression is equal to that. But now, what is the meaning of this term here? Well, this is exactly the residual that I observe when I compute the Newton CG step. This is observable. And what is this quantity here with a minus sign? The difference between the classical Hessian and the subsampled Hessian. So the residual of this idealized iteration has these two components. And now the reasoning goes as follows. When I control this error here, that's when I solve for this Newton iteration, doesn't it make sense to not solve this more accurately than this term here? Because if you solve this more accurately, you're not getting anything. The error in the Hessian is dominating the classic, the sort of step, the Newton-like step. So what we're going to do is we're going to estimate this error using sample variances. With that estimate, we can determine the residual, and that will control the number of CG iterations without us having to prescribe it. Okay, now I have a correct minus sign here. I will explain a little bit later how we do these variance estimates, but I claim that the difference between the sampled Hessian and the true Hessian can be estimated because this is the expectation of that, and because each function is a sum of terms. So I'm going to look at those variances. I can estimate that, and I set the residual that way. And then I don't have a fixed number of conjugate gradient iterations. Okay, so here's a theorem for the subsample Hessian Newton method. And it says, suppose that you have a strictly convex loss function. Why strictly convex? So you don't have to get into all the difficulties that Steve was mentioning about rates that change. So the idealized case, then regardless of the sample size S, and for any number of conjugate gradient steps, the iterates converge to the solution. This algorithm is convergent. Now, this may contradict. You say if you use a small sample size, this method may not be useful. How could it be that I have a theorem that works when the sample used for the Hessian can only be one? Well, I'm going to assume that each component function in the loss function, suppose that each component is convex, which is the case of logistic regression. So my assumption is not simply that that function is convex, but each one of these loss functions is convex. Therefore, if you take the Hessian of just one of them, you get a positive definite matrix, and the method is going to be convergent. So that's what the theorem says. You get a convergence result for a subsample Newton method, and it takes it away from the heuristic world into something that is a legitimate method. Now, should this be called a first-order method or a second-order method? Well, I talked a little bit about this. Something quite interesting is that this method is scale invariant. If you make a change of variables, the direction obtained by this method will be the same before and after the change of variables. Why? Because regardless of how many elements you took in the Hessian, they will scale in the same way that the gradient. What is not scale invariant, and I see many errors in machine learning papers, if you solve this system inexactly, you no longer get a scale invariant algorithm. The better you solve it, the closer to scale invariant it is. But it's very difficult to define such words. It's almost scale invariant. But if you solve it inexactly, you no longer get scale invariance. Okay, I want to just emphasize this idea by saying, could we apply similar concepts in the context of quasi-Newton methods? Is there a subsampled Hessian quasi-Newton method? And if so, how should it be designed? So we have an answer here, but maybe some of you can come up with a better answer. I'm going to assume that people are familiar with the limited memory BFGS method. It works like this. The method stores changes in the iterates. and changes in the gradients. And with that information, change in the gradients should give you an idea of the Hessian. It takes a step that takes an inverse of a Hessian approximation times the gradient. It looks like a Newton method. And then does a backtracking line search. It has to be careful. And here's the magic formula. These matrices H are updated. They're not built from scratch. You keep updating them as you go along by taking the new matrix is equal to the old matrix times these low rank modifications. So what is this term S transposed? It's a rank 1 matrix based on the changes in the iterates. And what is this Y that appears here? Changes in the gradients. So this magic formula gives you the so-called BFGS updating, which is tremendously successful, has been used in optimization for 30 years in all sorts of applications. You plug this formula in there and you keep updating things every time. How could I build a stochastic quasi-Newton method? Well, look at the structure of this updating formula a little bit more carefully, and we will be able to put subsampled Hessian information there. Okay, so if I have an updating formula of this form that gives you the relationship between the matrix at iteration k and iteration k minus 1, how about if we unroll this updating formula by expressing xk minus 1 in terms of xk minus 2 using the same formula? So if you do that, if you unroll it, and then you see what is the matrix that you obtain by starting with some initial matrix that I call 0 here and doing all these updates, the expression looks like that. So this is the nesting of many quasi-Newton updates on the initial matrix there. Now, in the codes that are around, limited memory BFGS codes, the initial matrix that you use for quasi-Newton updating is a very simple. It's a multiple of the identity. It's this quotient times the identity that I forgot to write here. And this quotient is the Barseline-Borwein parameter that Steve Wright mentioned. So you start with a very simple multiple of the identity matrix, and you update it m times, and you get a quasi-Newton matrix that is useful. You plug it in, and it gives you a nice iteration. The place where we're going to put the subsampled Hessian information is not going to be in the definitions of Y. Many people tried that. Shroudov, you others tried that. That's not going to be a good thing. The place that we're going to put subsampled Hessian information is in here. I'm going to pretend that this is a subsampled Hessian. And the trick is as follows. The step that you compute looks like the inverse of the Hessian approximation times the gradient. Now, when you look at the structure of the quasi-Newton updating formula, when we multiply the Hessian times the vector, times the gradient, here's the Hessian. I'm going to multiply times the gradient. How does it look like? Well, I take the gradient and it multiplies onto these terms, and then all of this multiplies together, and at some point, something hits H0. Something very complicated, but some vector hits H0 at some point. Okay, now let's pretend that H0 is actually a perfect subsampled Newton matrix. Suppose that it's the exact Hessian. So when at some point some vector q hits H0, I'm going to pretend that H0 was the exact Hessian. Here's the exact Hessian, and it's that vector q. That's the same as having solved the linear system of equations by bringing the Hessian to the left-hand side. And so I solve that system. Now, this is a Hessian times a vector is equal to a given right-hand side. Now suppose that this Hessian is defined by subsampled. It's a subsampled Hessian. So now apply the conjugate gradient method to solve this subsampled system using, again, maybe 1% of the information, and return that vector q that goes back into the quasi-Newton updating formula, then we come out of that complicated computation, and I terminate the evaluation of the Hessian inverse times the gradient. So in other words, the way this works is that inside we have a subsampled Hessian iteration that is never formed. But at the point that we need to touch it, we're going to apply Hessian free conjugate gradient method to touch it. And it's going to be surrounded by quasi-Newton updates based on true gradient information. It's sort of some mixture of full curvature information and some sample curvature information. And some of my colleagues tell me that this is a really nice idea, and this is a really, and then 6 months later, this is a really kludgy idea, and later that it's a really nice idea, and then it's a really kludgy idea, and it's come up with something better. So the thing is that it's not as clean as the Hessian free Newton method, but the results are just as good. So we tried that on our logistic regression problem, and we compared it with limited memory BFGS, and we can see that to obtain certain probability of correct classification, the numbers are quite positive, substantial decreases in CPU time. So this is a significant algorithm, but we have not implemented it in MapReduce. We've only done experiments in a sequential setting, which just is dynamic there. I hope all of you are going to be dynamic when you come after this workshop. How many of you are thinking of going to industry? How many of you are thinking of going to academia? And the rest of you are going nowhere. Starbucks is always an option, right? A lot more people want to go to academia than they want to go to industry. People, for some reason, like to be underpaid. I'm going to address this issue that I presented a method that doesn't start as well as a stochastic gradient method. So I want to shift now to an idea that is now natural. How about if we consider optimization algorithms that employ a variable sample size also for the function and the gradient? So when I was asked, where do you start, what sample do you use for the function and the gradient? How about if we start with a very small sample for the function and gradient, an even smaller sample for the Hessian, and keep increasing, start doing the optimization, and keep increasing both sample sizes as needed? Isn't that going to be more effective? I don't have to do a very good optimization towards the beginning. I only need to do accurate optimization towards the end. And I should be able to save a lot of work if I do this properly. Now, algorithms that do that have been proposed many times in the literature, and they're usually heuristic. Do 10 times or so on a prescribed sequence. OK, so we're gradually going to increase the sample size used for the function and the gradient. In the last half hour, I was concentrating on the Hessian. Now I'm paying attention on the function and the gradient. I want to mimic the stochastic gradient descent at the start, but without going into the twilight zone. I'm going to decrease the sample size, but not to the point of 1, maybe to the point of using a few hundred training points or maybe 1,000 training points. Not too much, and from there I'm going to increase things. And there are going to be two approaches for doing a dynamically batching algorithm. One, which is mainly favored by theoreticians, is that you predetermine the schedule at which the sample size is increased. And this is done because people can prove complexity results. The other one that, of course, we would like in practice is to adaptively change the sample size. And for that, we're going to use variance estimates. And I'm going to outline how this is being done. So remember that the objective function has a sum like this. Now, if we compute the gradient with a small sample x, it will just be a summation including fewer terms. And from now on, I'm going to call that gradient lowercase g. gk is going to be a stochastic gradient using a certain sample size that is monotonically increasing, but hopefully constant for some iterations. Then it goes up and constant. We're going to start relatively small and try to see if there are ways to increase it gradually. But now here come the big questions. I have a true objective function to minimize. This is the function that I want to minimize. If I compute the gradient of an approximation to this function, how do I know that the gradient is pointing downhill for the true objective function? And I cannot evaluate the true objective function because it's very costly. So my ideal objective function is the one that contains all the useful training points. I can't compute it. I take a subsample. With that, I compute a gradient. I keep optimizing with that gradient. And then at some point, some magic formula tells me, you're not making progress with respect to the true objective. Therefore, increase the sample size. Keep minimizing, and then it will say the same thing over and over, and then you keep increasing things. How can you possibly know what you're doing on the true objective without computing it? Well, we're going to have to do some statistical estimates. It's a stochastic function. And maybe the way we started thinking about this is something that you might actually buy. You might find it reasonable. When I compute a stochastic gradient, that stochastic gradient itself is the sum of components. If it weren't, I wouldn't be able to say anything. But this gradient here is the sum of the gradients of the loss functions. Now, I'm going to look individually at these gradients and consider their variances. And I'm going to say, when I compute a particular gradient here, how does the norm of that gradient compare to the variance I observe in the components of the gradients? If this sample variance is bigger than the norm of the gradient, I'm not going to trust it. Now, this is not the way I'm going to build the algorithm, but this is the motivation. So when I compute my direction, the variance is just as big as the norm of the gradient, I'm going to say, OK, that's not accurate enough. Increase the sample size. And why is it reasonable to think this way? Because as we optimize a function, the gradient will converge to 0. But the sample, the standard variation of its components, will not go to 0. So I have the true objective function that I want to minimize. And instead of that, I work on another objective function, a stochastic approximation to that. I decrease that objective function. As I minimize it, the gradient of that function goes to 0. But the variance of the elements forming it do not. So at some point, I'm going to cross the two conditions. The variance is going to be higher than the gradient, and then it's going to tell me to increase the sample size. I start minimizing some other function, and I keep going that way. That's going to be the idea on which I will build things. And after the break, what I'm going to do is, it's going to be now, after the break is going to be applications. So I'm going to tell you, well, now we have subsample Hessians, Newton CG, dynamic sample sizes. How do I apply it to regularized problems? How do I apply it to matrix problems? And how do the results look like? And some of the results I'm going to present here to you are some results that surprised me. Because methods that were considered to be the natural thing to do for large applications are going to be losing by a factor of 10 or 100 to methods that incorporate second-order information in the applications that I will give you. So the talk will finish with such information. Let's take a break now, and so we'll come back at 10:30.